Yeah, I would say let's get started. Maurizio, you have hit the record button. So let's continue with the second lecture on neutrino astronomy and astrophysics by Foteini. And please, Foteini, whenever you're ready.
Okay, thank you. So thanks to everyone who woke up and who's interested in the astro side of neutrinos. I'm happy to see that there are many of you here. Yesterday we spoke about the experimental concepts, and today the topic, it's going to be much more theoretical and also thinking about astrophysics. Okay, so we were left off yesterday discussing the requirements on the accelerators of these high energy neutrinos, and we only covered yesterday what is the minimum requirement of confinement. So which kind of sources we can imagine can confine cosmic rays to high enough energies so as to reach these energies of protons that ice cube eventually sees through neutrinos. So today we will continue with those requirements on the accelerators. And first we will look at the possible connection of ultra high energy cosmic rays to neutrinos and what that means in terms of the expected neutrino flux if the sources of those two messengers are the same. And then we look at the energy budget of the sources and the source number density that we can infer from the ice cube observations. Okay, so in order to, what we're going to do when I say we're going to predict the neutrino flux that we expect based on the ultra high energy cosmic ray flux that we observed. And the idea here is that in the 90s, we already had a flux of ultra high energy cosmic rays that we observed, but no neutrinos. So this was a prediction made in the 90s. And in order to do this, to work through this here, I have to introduce a few concepts, starting with the energy losses of ultra high energy cosmic rays. So just a bit of definitions here. So when I write lambda, I mean the mean free path between interactions of these cosmic rays. Let's assume that they are in the universe and they interact with background photons, which are shown here. So primarily the cosmic microwave background, but there are all kinds of other backgrounds as well, from the collective emission, all the stars and all the galaxies and the history of the universe. And so lambda is the mean free path, and it's defined as 1 over the number density of photons, the targets, times the cross-section for the process. Then the energy lost per unit time is equal to the inelasticity, which is kappa, times the cross-section, times the number density, times the speed of light. And the inelasticity here is just the fraction of energy lost per interaction. So with this quantity, if we take the inverse of this quantity, which has now units of time, and we multiply it by the speed of light, we basically get an idea over what propagation length a cosmic ray loses all its energy. And so here, the two processes are important for ultra high energy cosmic rays. First of all, they could interact with a photon to produce an electron-positron pair. So this is a process which has a small inelasticity of order 10 to the minus 3. And here I wrote the cross-section and the number density of the CMB photon. So then we can calculate that the mean free path for interactions is about 1 megaparsec. And since the inelasticity is 10 to the minus 3, if we divide the mean free path by the inelasticity, we get that the energy loss length is about 1 gigaparsec. So if we divide this by the speed of light, we basically get the lifetime of these cosmic rays. And the threshold for this process now in the lab frame, if we have CMB photons, is roughly 10 to the 19 electron volt for the proton. So below this energy, there is no photopair production. So is this there is a question, is this the relativistic formula? Here, yes. I mean, for the energy loss, this is just a general formula. But everything that I've done here, actually, I haven't shown the full calculation, but this is relativistic, yes. Okay, Aman? Unless I hear otherwise, I continue. So now we also saw yesterday the photo-pion production process, and here just to remark, I think yesterday I didn't say it, actually how this process proceeds is that we have the production of the delta baryon, the delta resonance, and then it decays to either a neutron and a charged pion or a proton and a neutral pion. And here the inelasticity is much larger. The proton loses more of its energy, about 20%. And if we are above the threshold for production of this pion on the CMB, then the proton needs to have in the lab frame again of order 10 to the 20 electron volts energy. So this process kicks in quite late. And then the losses are very severe. The interactions are very frequent. So within about 50 megaparsecs, the proton is basically stopped, or it has lost a lot of energy. And here, for those of you who are not astronomers, I put what do these numbers that I quote here of megaparsecs mean? So roughly speaking, the nearest galaxy is at about 1 megaparsec. For more rare sources like Blazars, which we'll look at today, the nearest one is at 100 megaparsec. And then when we talk about cosmological things, like, for example, the redshift at which we had maximum star formation, the distance is of order gigaparsecs. Okay, so why I said all this is that we should remember that below the threshold for photo-pion production, cosmic rays have a lifetime of about a giga-year, few giga-years, or a loss length of a gigaparsec. So now we're going to look at the ultra-high energy cosmic ray spectrum. This is the spectrum that is measured by the Pierre Auger Observatory. This is the highest energy part of that spectrum, and we see here the cutoff. And we're going to use this to estimate the energy density in ultra-high energy cosmic rays. So this plot is again in bizarre units of the flux. This is now E cubed times the flux of particles, J. Often you will see this as a phi, and we'll switch to that notation phi later, so please bear with me. Here we call it J, and J is the measured number of particles per unit energy, per unit area, per unit time, per unit solid angle at the Pierre Auger Observatory. And now, in order to calculate the energy density of cosmic rays in the universe, we're going to do what I consider a rather neat trick, which one always needs to do in this field. So the number density of particles, we can define this as the number of particles per unit energy per unit volume. And we can write this volume as per unit distance, L, per unit area. And then the unit distance, since these are relativistic particles and we want to know how, the number density in a given volume, they travel at the speed of light. So we can express this as the speed of light times dt. So now we have something which looks quite similar to that flux up here. In fact, it's equal to J times 4 pi, and the 4 pi comes from the fact that we integrated over solid angle. We assume that these are isotropic. There is a question I see. Are we neglecting photo disintegration since we're only considering protons? That's right, Simone. So we're only talking about protons today. It's an interesting thing, but this calculation was done at the time when people thought that everything up here was protons. And this is why the calculation started here, because we knew that at lower energies there were nuclei. But actually, we're going to see how this compares to what we know today in a moment. Okay, so so we ended up with this expression for the number density, and always remember this factor of 4 pi over c. It will come up always in your calculations when we convert from number density or energy density to flux and vice versa. So now we are in a position to calculate the energy density of ultra high energy cosmic rays, which is just an integral of that number density times energy times the E. And so I'm going now to do a simple calculation using this, what we see here. So I actually took the flux at some energy E naught. What exactly that is does not matter. I took this point here, which is the angle of the cosmic ray spectrum. And let's integrate over roughly 1 decade in energy. And so I did this to keep the integration simple. So then I also assumed that we have an e⁻² spectrum, which is not the case. As you see here, Auger actually measured something like 2.5. But with these simplifications, the integral gives this. So this ln E max over E min comes from assuming it's an e⁻² spectrum. And since we're integrating over 1 decade in energy, we get this ln 10. So the energy density is then 10⁻⁸ electron volts per cubic centimeter. That's the energy density of cosmic rays. And now if we convert to Gaussian units, the unit of energy here is the erg, and that's about 1 TeV. 1 erg is about 1 TeV, or 10⁻12 electron volts. Okay, so we have now the energy density, and with this we can calculate the energy production rate of ultra high energy cosmic rays. So we divide the energy density by the lifetime of these cosmic rays, which I said is about a few gigayears. So if we put in these numbers, we get the energy production rate to be of order 2 × 10⁴ ergs per cubic megaparsec per year. That's how much energy we need to power all the cosmic rays that we observe in the vicinity of the Earth. And I was very pleased when I did this calculation, because it's actually very close to what one obtains when one does the calculation properly using the intrinsic spectra at the sources, and the fact that we now know that not all the cosmic rays are protons, and they're in fact nuclei. So we're a factor of 2 away. So now we have the energy production rate of ultra high energy cosmic rays. Now we can calculate the expected neutrino flux from the interactions of these cosmic rays. And what's important is that now we're thinking of the interactions of these cosmic rays inside their sources. So let me quickly rearrange the zoom. Okay, so I'm going for simplicity to drop the factor of 2. Actually, the original calculation that was done by Waxman and Bahcall in the 90s said, let's say the energy production rate is 10⁴ ergs per cubic megaparsec per year. And now to convert to the expected flux of neutrinos, we remember that 1 neutrino takes roughly 1/20th of the parent cosmic ray energy. We have this factor of c over 4 pi because we're going to convert back to a flux. We integrate the production over the 1 Hubble time. This is the TH here. Then we have another factor which relates to the redshift evolution of the sources. So redshift, the sources that were more numerous in the past have a factor of xi, which is larger than 1. It goes up to 10, depending how rapid the evolution was. And it can be as small as 0.6 for sources which do not evolve. Then we have a factor of 1/2 because we're interested in the single flavor flux. In fact, the flux of muon neutrinos, and about 50% of the energy of the pion after it decays goes to muon and anti-muon neutrinos. And then we have another factor of 1/2, which comes from the fact that 1/2 of the pions are neutral pions, and they produce gamma rays, and they don't contribute to this process in these big gamma interactions. So, and then we don't a priori know what fraction of its energy the proton loses, but let's assume it loses some fraction epsilon, which can be as much as 1. So if we set this number to 1, then we get an upper limit to the neutrino flux expected from ultra high energy cosmic rays. So let me go now to the next slide where I plot this is the numerical value that is obtained from this calculation, and psi will leave it out, and eta epsilon here is set to 1, and we see we use this benchmark more or less. We use the cosmic ray flux more or less in this energy region for this calculation, which I've denoted with the dashed line, the dotted line. And the Waxman-Bahcall flux is shown here in pink. So this is for sources which have a rapid redshift evolution, and sources which do not evolve are shown down here. So basically we have a kind of range, which allows for the fact that we don't know a priori which sources will produce the cosmic rays and the neutrinos. And what's very interesting is also, again, as I said before, this was done in the 90s. Now, if we look 20 years later, this is the flux that IceCube measured, and it falls really beautifully into that band. So many people are very pleased to see this, and this may be because the sources of the ultra-high energy cosmic rays and neutrinos are the same. It may also be just a coincidence that we have another type of accelerator with a similar energy budget. Okay, so now let's switch to thinking about neutrinos, forgetting the connection to ultra-high energy cosmic rays. And here we're going to, again, use the measured flux of neutrinos to establish the energy budget of the neutrino sources, forgetting now about cosmic rays. And that will help us also say something about the number density of the sources. So we're going to use, as we did before, the idea that we can derive the luminosity density or the power density of the sources from the measured IceCube flux. And that we can parameterize. Now, if there were many astronomers here, they would be very angry with me, but we're going to do this very simply by assuming that there is a particular average luminosity, which represents the population of sources L, and this is the neutrino luminosity, which is typical for the population, and N is the number density of the sources. And N is a quantity which we measure with astronomical surveys, and here I have the values for several different objects, so we know that normal galaxies are about 1 per 100 cubic megaparsecs, and things which are very rare, like flat spectrum radio quasars, which are the most powerful active galactic nuclei, there is only 1 per about gigaparsec. So now we can use the number density of a population to say what is the volume within which we typically expect one source. And this is this equation here. It's basically 1 over the number density. And we can use this expression, and this is spherical volume, so R is the distance, to derive an expression for the distance of the nearest source of that population. So basically, we write now the same equation in terms of R, and we find that if we have a number density, the population with number density N, then the distance to the nearest source should be on average 4 pi times N over 3 to the power of minus 1/3. What does this mean? If we have a number density, if we have a population, let's say jetted AGN, which are 10 to the minus 4 per cubic megaparsec, what the nearest distance I would get with my small calculation here is 10 megaparsecs. And I don't know, does anybody know or want to write in the chat the distance to the nearest radio galaxy, jetted AGN?
Take a guess if you don't know it.
Okay, everybody's very shy. 12. Actually, it's 4. That's the one that came to my mind. It's radio galaxy Centaurus A. Of course, this is just an average, what we're doing here. And that source is thought to be a great candidate for producing all kinds of high energy particles, but thanks for taking a guess. So now, okay, let's go a little bit further with this thought here, and just to proceed to say that if we have a source with neutrino luminosity L at the distance R, then the flux we expect is just L divided by 4 pi R squared. And we can use this simple formula to say, we know yesterday we saw, oh, there is a question. Let's see. Is the statistical uncertainty large on the number density for every source, or is it well characterized? Karen, thanks for this question. Actually, in reality, there is some uncertainty, which has to do with the limit of a particular survey. That means the fainter sources below the limit of the survey, we cannot know them. Normally, we can extrapolate because we see how the luminosity of each population behaves at different redshifts. There is some uncertainty, but when we think about neutrinos and very powerful sources, I think in general, we don't have to worry about this uncertainty. It's generally natural that the more powerful sources would contribute first. Okay? So there might be some unaccounted for sources, but I don't think our first guess for where the neutrinos come from should be the faintest source. It may be the case. Okay, good. So now I wanted to use this simple expression for the flux for from a source with luminosity L. And the fact that with ice cube, you might remember this plot that I showed yesterday as a function of declination, the sensitivity of ice cube. We have a sensitivity limit. We know what is the flux which we can detect. And if we detect nothing, we know that the flux has to be below that. And that's the F lim that I write here. So we can write now this expression substituting this F with the limit from ice cube and rewrite it in terms of the distance R to say that if we have a source with a particular luminosity and we haven't detected it with ice cube, then that source has to be further than R. Otherwise, we should have seen something with ice cube. Okay, so now we have one expression here. We have another expression for the distance of the nearest source from a population, which we derived before as a function of the number density of the sources. And we can combine these two equations to get an upper limit on the number density of the sources for a given experiment with a given F lim as a function of the luminosity of the sources. Okay, so basically that's the limit. So the sources have to be few enough if they have a particular luminosity L, that there's none of them near enough to us that we would have detected it already with our neutrino detector. And this F lim is different for different types of different detectors, and even it changes with time. So as ice cube gains exposure, this limit goes down. It improves. Okay, so now let's go to this plot and basically, oh, there is a question. Yes, the question is, does the number density change with time? It does for almost all the sources that we know. So for example, the most powerful blazars, which we're going to look at later today, have a very rapid positive evolution. That means there were many more of them in the past. But the weak blazars, there are more of them locally. So they have a negative redshift evolution. That means there is more of them. The number density is larger nearby or at small redshifts. Okay. And most sources have a, well, actually, that's not really true. I wanted to say that most sources follow the star formation rate, but that's not actually true. Many of them do. Okay, now what we have here is the number density of different types of sources times the luminosity in neutrinos. And any source which produces sufficient flux to produce the ice cube neutrinos should sit on this red band here, and the band has a width because of the redshift effects, the redshift evolution of the sources. So the number density we measure with surveys, and basically that would define for any source a line on these axes. And if we have sufficient power as to produce the neutrinos, we should be sitting on this band here. So if we're above it, then we would be overproducing what ice cube sees. And if we're below it, then we just cannot, these sources cannot produce the ice cube signal. They don't have sufficient power. So here, what we see down here are the most powerful sources. They are relatively few and rare, and up here are more common and less luminous sources. Okay, and we previously derived a limit on the number density of the sources, which is luminosity dependent. So that limit shows up like this. We can rule out that there exist neutrino sources of a given luminosity with number density larger than something, and that is shown with its gray band. So that gray band cuts into the parameter space in this way because of the -3/2 dependence on the luminosity. And it basically tells us that the neutrinos that we see in ice cube cannot be coming from the most powerful sources. So in a way, this is a very important result. It may be also disappointing because it's easier to find neutrinos if they come from a few very powerful sources. And just to finish with this, if in future we have another experiment which is more sensitive than ice cube, eventually that limit moves in this direction. So we will be able to rule out more and more of these source classes and get into more and more ubiquitous sources that will be able to constrain them. Okay, so that brings me to the end of what I wanted to say about constraints, generic constraints on the sources. So we saw that okay, the neutrino sources must have a sufficient energy budget. Somehow I didn't go too much into this, but generally this is not a problem. Based on what we see in terms of photons, if the energy budget in neutrinos is similar, then most of the sources we have considered so far would make it. Then we looked at what would be the predicted flux of neutrinos if they have a common origin with ultra high energy cosmic rays. And interestingly, that flux coincides with ice cube, with what ice cube sees. And then finally, we looked at the constraints on the number density and the fact that the neutrinos we see in ice cube must come from sources which are not too rare and luminous. Otherwise, we would have detected point sources already with ice cube because of this quantity F-lim, which is the limiting sensitivity of ice cube. Okay, so now I'm going to switch and talk about individual source classes.
Foteini, can I ask you a question before?
Yes, please.
Yes, sorry. Yeah, I got curious about your figure 17. Sorry, slide 17. Yeah. I've seen this plot before, but I just noticed that there are some thin lines, right? Like you notice the thick dashed blue lines. They're also next to it, thin dashed blue lines with a different slope. And I'm interested in, I mean, how do you get a different slope? That's coming from your previous estimation of n, right?
So I guess, I think Marcus is probably better than me to discuss this because he's made this plot himself, but I think it's two different limits here. So there is one limit which comes from the point source sensitivity, which is what I discussed. and one which is from the multiplets, but actually probably Marcus can comment better than me on this.
So you're absolutely right. So that you can also approach this with not with the point source limit, but also like stacking limits, for example. But if I remember correctly, the difference, the tiny difference that you see there on top, so underneath your cursor, this is coming from the fact that at these very low densities that you have here on the bottom, you basically have the closest source on average sitting at already quite large distances. And so you have to take into account luminosity distance effects. And then this estimate that you show, this was based on a Euclidean universe. If you include redshift, you can modify the argument a little bit to account for luminosity, and then you get like different shapes that deviate from this distance to the power -3/2 behavior.
Yeah, that makes sense.
Okay, that makes sense. Yeah, thanks, Marcus.
Thank you. Yeah.
Okay, great. Okay, so then let's talk for the remainder of today about active galactic nuclei. And I wanted to start with a general introduction to what these very impressive objects are. So this is a picture of an active galactic nucleus shrouded in clouds of dust, which is quite common. So each of these sources is about 1,000 times brighter than a typical bright galaxy in the universe. And the reason why we call them active is because the luminosity that we see from them cannot possibly be coming from stellar processes only. There must be another source, and most likely that's accretion to a central supermassive black hole. You might have seen in your undergraduate lectures these spectra. Just a reminder here that this is a normal galaxy, some emission lines related to hydrogen, but quite narrow. And then when we see the spectrum of an active galaxy, we see these very broad emission lines and very strong, and they tell us that there is very rapid motion in this source. So about 1% of galaxies have these active supermassive black hole, and we see them out to very large redshifts, up to 7.5 in redshift. So now let's briefly think about what is the engine of these sources. Here is an example of a spectrum of an active galaxy, which has what I will claim is most likely an accretion disk. This is a UV and optical radiation. And so the power that we see in these galaxies is of order 10 to the 46 ergs per second. That's the luminosity. And so the easiest way that we can imagine that this luminosity comes about is if we have matter accreting onto the black hole. And in this process, about 10% of the rest mass energy of the infalling matter is converted to radiation. So if we now rewrite this equation in terms of this mass infall rate, here is the luminosity which we require the source to produce, and we divide by the efficiency, which is 10%, we get that we need of order 2 solar masses of material per year in order to power one of these powerful AGN. So actually, this is not a lot if we consider that in these galaxies there are, of order 10 to the 10 solar masses of matter. But there is a but here, and this is that matter cannot radiate at any luminosity, and that is the Eddington limit. So in order for an object to continue to be bound by gravity and not be blown up by its own radiation pressure, we have a maximum luminosity with which a source of mass m can radiate, and it's given by this formula, where here we have the Thomson cross-section. This comes in because the radiation pressure comes from the electrons, and we have the gravitational constant here. So for a typical, for an object with the mass of the sun, the Eddington luminosity is 10 to the 38 ergs per second. And we need of order, 8 orders of magnitude more luminosity in order to power an AGN. And this lets us know that we need a humongous mass. And that is very likely the supermassive black hole, because we also know that we need this all to be in a compact region because of the rapid motion and the broad lines that we observe. So we see AGN in many different categories, and people classify them in many different ways. But there is what we call the AGN Unification model, which aims to describe all the AGN that we observe based on a few characteristics. One is whether they have a jet or not. So in this picture, there is a jet, but there are also AGN that don't have the jet, and only 10% have a powerful jet. The second characteristic is to do with orientation, whether we see the AGN from the side. So if we have a jetted AGN, that would make what we call a radio galaxy. And if we're looking directly into the jet, that's what we call a blazar. And then it also, another important criterion is whether there is emission, which is close to the Eddington limit of a supermassive black hole. That's what we call radiatively efficient. Or not, whether the source is radiating at sub-Eddington powers. So, and they are, in my opinion, really beautiful objects to look at. These are radio galaxies of 2 different types. Basically, we can, if we now focus only on the jetted AGN, we see them either with jets, which are very collimated out to very large distances. There is a question, are radio galaxies the same as quasars? Yes, but when we say quasar, we must be looking at it into the jet. But what I'm claiming is that they are the same, and this is a very popular model. There are a few small sticky points with that model, but it's a very widely accepted idea. Okay, so now we have these very powerful types of jets. We also have what is called Fanaroff-Rayleigh type 1 radio galaxies, jetted AGN. And they don't have these very collimated jets. The jets you see here turn into plumes at large distances. So when we have a blazar, and some blazars are quasars, that the question was, not all of them. Unfortunately, we don't see pretty pictures, so we see what looks like stars, point-like sources. And so it took a long time for people to understand that these were actually objects at cosmological distances, and that they were active galaxies because of this star-like appearance, but they have really impressive variability. So in terms of flux and timing, we see very interesting properties in the light curves, or sometimes we can have a spectrum. Okay, so to proceed with this, and we're going to think about whether, blazars specifically, but also jetted AGN are good sources of neutrinos. So to proceed with this, yeah.
And on the previous slide, is this all the same object, or are these different?
No, they are different.
So these are different quasars that you're looking at? Yes. Okay.
I just found the pictures that I liked the most. Yeah.
Oh, okay. Just thank you.
Yeah. Okay. So I wanted just to give a brief reminder of relativistic beaming, because when we look at the blazar, in fact, what we're looking at is an emitting region which produces light, which is traveling at relativistic speeds towards us. And actually, it took quite some time for people to notice that normal special relativity does not apply in this case when we're dealing with relativistically moving light. So in typical special relativity, we have, if we have a region moving with Lorentz factor gamma, then we, as observers, we measure lengths which with respect to what is measured in the proper frame are contracted by a factor of gamma, and the time is dilated by a factor gamma. Now, when we have a blazar, we have something which moves at close to the speed of light in our direction, and what we see is the effect of relativity plus Doppler, usual Doppler effect, and we get a factor delta in the equations, which is the product of these two effects, special relativity and the Doppler effect. And basically we get a very strongly boosted emission if we're sitting somewhere in a very small angle to inside the line of sight of the jet. This is shown here. And if that angle, so if we now move away from that line direction of the jet, we have slowly, we lose that boosting, and in fact we have deep boosting at large angles. So here I wrote all the relations, but if we concentrate on the luminosity, so the luminosity that we observe is basically boosted by a factor of delta to the fourth with respect to what an observer who is at rest with respect to that moving jet would measure. And in a blazar, typically the Doppler factor is of order 10 or 20. So you see that we get quite a significant boost as observers. Now, just because we're going to come to this on Friday, GRBs have actually factors here of order 1000. So we are, this is also something to keep in mind, and we'll come to this on Friday. So I explained that the emission that we see is not actually what the blazars do. It's an effect of beaming. And this partly explains why when we look at the gamma ray sky, basically everything we see outside our own galaxy, this is the galactic plane, and these are all the sources that the Fermi satellite had measured in its first 5 years of operation. They are all blazars. And this is the same if we look at higher gamma ray energies. So then we need instruments on Earth to have a big enough collecting area. And we know a little bit less than, but of order 100 blazars, which are all the red dots. And again, all the sources that we observe, almost all of them are blazars if they're extra-galactic. And in the galactic plane, we have supernovae and pulsars. And this is what the blazar typically looks like if we look at it with many instruments, from radio to optical to X-rays to gamma rays. We see these two bumps in the spectrum. And just to briefly say that since we saw that there are two types of jetted AGN, there are also two types of blazars, and I think, and most people think that this is a direct connection between these jetted AGN and blazars. So what we see in the optical spectra is a disk, a powerful disk in the case of what we call flat spectrum radio quasars. And in the weaker type, which is called BL Lac objects, we don't see a disk. And we think that, so I'll come to this in a moment. This is interesting from the point of view of neutrino production, this difference. What actually might be happening when we see these flat spectrum radio quasars, except for the fact that they have this powerful jet that I already discussed, is that the accretion disk is radiating at close to the Eddington limit, and we also have gas clouds surrounding the accretion disk. So that makes for a region where we have strong radiation fields, and potentially, if you think about neutrino production, we need to have some kind of target. In AGN, probably the most promising target is such dense photon fields where we can, protons can interact to produce neutrinos. Now in BL Lac objects, there are not so many photon fields around the black hole. There are the photons from the jet. So there are still options. So let me go briefly into the emission from blazars. That will lead us to understand a bit what the neutrino production might look like. So we see these two bumps in the spectrum. And more or less everybody agrees that the first bump is just synchrotron emission from some population of electrons with, originally you have one power law, maybe after inside the source there's some cooling that can change the broken power law, we get synchrotron emission. Actually, I have put in the backup all the equations, but I will not go through them in detail now, which tell us given and observe, what we observe, the synchrotron emission, what energy we observe it to peak at, we have an expression which depends on the magnetic field of the source, the Lorentz factor of the electrons, and the Doppler factor of the blazar of the jet. So just keep this in mind for now, but basically what we think we have is just one, for simplicity, one region moving relativistically down the jet. So then we have another bump in the spectrum, and what we think this second bump comes from in the simplest models is the same population of electrons which have produced synchrotron photons interact with those photons, they get inverse Compton upscattered, and they produce this high energy emission. They gain energy from the interaction with electrons, and they produce this upscattered emission here. Now, you might remember this is the formula which gives us the average energy of an inverse Compton, the frequency of an inverse Compton upscattered photon if the Lorentz factor of the electron was gamma b. And here we are saying that the photons are actually these photons here. So they have frequency nu s. So I just say this to show that actually now we have two equations which give us gamma b. In fact, if you look at later at your leisure, at the back of slides, we can learn quite a lot about the properties of the emitting region of this blazar because of this fact that we have two handles on these quantities. So this is interesting when we want to do neutrino calculations, and it's not always there in other types of sources. Now, in flat spectrum radio quasars, we don't think that this is the same. We think that the second bump might be, again, inverse Compton emission, but in this case, coming from interactions with photons close to the black hole. Let me go. Okay, we have about 10 minutes more. So here, what I wanted to say is so far I didn't talk about protons, but it's reasonable to think that protons are also accelerated in these blazar jets. And in fact, if we put in the values for the magnetic field strength and the radius, which we infer by doing this, by assuming this synchrotron and inverse Compton on the synchrotron photons, we get values which would lead us to think that we can easily accelerate ultra high energy cosmic rays in these sources. So certainly sufficient energy as to produce PeV energy neutrinos. So what might be happening in the jet might look something like this. The protons interact with photons, either photons from the jet or photons from the fields close to the black hole, and they produce again similar amounts of neutral and charged pions. And the neutral pions produce gamma rays, the charged pions produce the neutrinos. So this allows us to set the relation between the luminosity of produced neutrinos and the luminosity of produced gamma rays from these P gamma interactions. And it turns out that they're really comparable. So here there is a factor of 3 from the fact that we have 3 neutrino flavors. There is a factor of 1/2, which comes from the fact that each neutral pion decay leads to 2 gamma rays, and a factor of 1/2 because each gamma ray produced in neutral pion decays has about half the energy of a neutrino produced by a charged pion. So we have a relation between the gamma ray and the neutrino flux of any source, And since we measure the gamma rays from all these sources, I showed them before with Fermi, with TeV instruments, basically we can get an upper limit to the neutrino flux from any source just by looking at this gamma ray flux. And now another thing which tells us about what kind of neutrino spectra might be produced by these sources. So in these big gamma interactions, we have a cross section which is peaked due to the resonant, to the delta resonance. And then we have a photon spectrum. Now, I showed several blazars and their photon spectra looked something like this. In this plot, there are just many different blazars. And I show underneath another plot which actually shows, here we're looking at energy flux, but down here we have a number density. So this is the number density of photons in a source which has this kind of energy flux. Now the neutrino production efficiency basically depends on the cross section for the process and the number density of target photons. So in reality, we have a process where the higher energy protons have more photons to interact with, and because of the cross section which has this resonance, basically what the product of this is that if we have a proton spectrum which is a power law, we do not get a neutrino spectrum which is a power law. We get a neutrino spectrum where the neutrino production efficiency increases with energy because of this. So that you see that it's the inverse, it increases as the inverse of the density as we go up in energy. So we end up with very peaked neutrino spectra from AGN. Okay, so let's use this, and now we can look at, in this plot, what is shown is the neutrino energy spectra from different authors. So the red and the blue and the green lines show neutrino spectra that were predicted long before IceCube had made any measurement of neutrinos, some of them in the 90s. And they were predicted to come from all the AGN, all the blazars in the universe. And we can remark several things. Here is the neutrino flux that we now know IceCube measures. But what I wanted to highlight here is, okay, first of all, we can already say that we can rule out these models. The most optimistic one of them is because they overproduce we don't observe such neutrinos, so many of them. We could say that we have to scale the models down, just pushing them down in this plot. But the other thing is that all these models have a peak neutrino energy, which is at around 10 to the 17 electron volts, 10 to the 16, one of them. And that's much higher than the energy where all the IceCube neutrinos are. So I will show just one final slide. Maybe we'll look at that slide again on Friday to start the final part of the discussion on AGN. And this is that we can do another thing, and we know how many blazars are in the universe, more or less. We don't know all the faint ones, but the bright ones, there are a few thousand of them. And we can look at the directions of all those bright blazars and see if there are neutrinos that IceCube sees in the direction of those blazars. And this is what has been done inside IceCube. And in fact, there are no neutrinos coming from those blazars. So this allows us to put an upper limit to the neutrino flux from blazars in IceCube, and that limit is of order 20% of the total flux. So this to you might sound natural now that I've said all this, but many people are very unhappy about this because blazars, you might see here, people had such high hopes for blazar neutrinos in the early days, and because of this picture that we saw before, where we thought, maybe all the messengers come from the same sources. So we saw before the Fermi sky map, and basically all the gamma rays we detect, more or less all of them, the extra-galactic ones come from blazars. But unfortunately, this cannot be true. So blazars cannot be the sources of the ice cube neutrinos in this energy range. It's still possible that maybe there is another population here. And for the ultra high energy cosmic rays, we don't know. So I'm going to stop here, and then on Friday, I will just briefly talk again about blazars and also the possibility that they may be transient sources of neutrinos. So blazars undergo very strong flares. So we'll first look into that and then discuss starburst galaxies, tidal disruption events, and gamma ray bursts. Okay, so there is a question. Have people thought about the possible cutoff coming from non-standard interactions of neutrinos in the blazar spectrum or in the ice cube spectrum? In the blazar spectrum. I'm not aware of this, but maybe Mauricio, if there is something, maybe Mauricio.
Yeah, I guess you mean, Jaime, why are these blazars not making the high energy neutrinos, and a beyond astronomical explanation for that? And people have thought of that, like if you have neutrinos disappearing along the way. So if blazars do make this TeV to PeV neutrinos, but they don't reach us, that could be due to neutrinos interacting along the way with something, and that's extra interaction would be beyond the standard model. People have thought about that in the context of secret neutrino interactions, which are interactions of high energy neutrinos with a low energy relic neutrino background from the Big Bang. It is certainly possible, but it's difficult to falsify at this point. So maybe with more data, you can see extra features that could lend this possibility more make it more interesting. But yeah, it is in principle possible, but it's a bit convoluted at this point. We probably want to go for the easier explanation without any BSM and just say these blazars are not making high energy neutrinos.
Foteini, can I ask you a question about the previous slide? So yeah, so you mentioned here this, so HZ, I think this is Halsen SAS.
Yes.
Do you want to comment? I mean, if you also talked about the Waxman-Bahcall bound here, which was basically at the level of the ice cube flux. I mean, is this consistent with the Waxman-Bahcall limit that you derived?
Okay, I understand your question. Actually, I don't know the details of this Halsen and SAS model, but I can comment on the fact that it's possible to have more neutrinos than we have ultra high energy cosmic rays. If the cosmic rays that we measure outside the sources are, fewer than we have inside the sources, so we have hidden ultra high energy cosmic rays for whatever reason, maybe they cannot escape the source. So I would guess that this model utilizes that effect somehow. So the Waxman-Bahcall calculation, we assume that the proton content of the sources is the same as what we measure. Marcus, do you agree that this is probably?
Yeah, so you need some loophole in the argument of the Waxman-Bahcall limit, and I guess what you mentioned is the one that for some reason not all the cosmic rays escape, and so you can have a inflated population of those in the source.
I will check that paper. I must admit, I don't know, but yeah, that's an interesting point. Thank you.
Thank you. Are there any other questions? We can maybe also now, so it's 11, so this is the start of our coffee break. So I hope Foteini is also available to join us in Gathertown, and there will be also then the chance to ask more questions. So maybe we should thank Foteini for this nice lecture this morning. Let's go for our coffee break, and then we will return at 12:30. I think it's 12:30, right? 11:30?
It's 11:15.
It's 15 minutes break. So it's 11:15 with the next lecture on neutrino cosmology by Olga. Okay, see you in a bit.